Good morning. Um, we have made our way through chapters 27 and 28. We have looked at the magnetic forces and magnetic fields. And for this last lecture from chapter 28, I guess is how it's listed, I wanted to go back and do another set of reviews for some homework examples. I feel like talking through some of these problems and especially focusing on how they're set up and how to bring the formulas in, how to identify how to set up some of the integrations. I think these are handy things to talk about. So let's go ahead and get started. I've got quite a list of homework problems that I put together, so I don't know if we're going to get through all of them. Anyway, I started with back in chapter 27 when we were looking at magnetic forces. So what we have in problem 9 is we've got a magnetic field. Now, the book likes having the magnetic field come out of the page. I think it's easier to have it go into the page. It doesn't really make a difference. Anyway, we've got a magnetic field. We have current, which is traveling. I guess the current's drawn right here and here. So we got current going through this loop. There's only one loop. As I always say, I always lose the number of loops, so I always got to check, and even if it's one, I got to remind myself. So what's happening is I've got current going through this. Now the magnetic field extends up to here, through this mid-region and down below. In the problem, only this line is given. I put in a matching line down here, and let me show you why. Because when we get this current going around in a circle here, what that's going to do for us is we're going to end up with forces. So if we look at the, if we use a right-hand rule, thumb in the direction of the current and fingers in the direction of the magnetic field, then, so there's the current, there's the magnetic field, something like that. Then the palm is facing in the direction of the force. So the force is outwards, radially, away from the center, except that there's no force in the region where there's no magnetic field. So if the magnetic field were everywhere, by symmetry, all these forces would cancel out, but this part's missing. Now, we could go in and carry out an integration, and that is what we have to do because we've got these forces in different directions. We're going to have to break them up into components. That's an example, right? If I've got a force down in this direction, I need to designate an angle, take a sine component, a cosine component, and then add together the net force in the x and y directions. Now, what I realized when I looked at this problem was, if I do a mirror image down here and draw this line, even though I've got magnetic forces here and here, they're going to cancel. So now I've got a symmetric setup where these side sections, at least, the forces from those, they're going to cancel each other out. I don't really have to go through and integrate all those. So this part is missing, but this part is here. If I just integrate from theta naught to theta naught, negative theta naught to positive theta naught, that should do it. So for the net force, I said I'm going to add together all the df's, and I'm actually only going to keep the cosine theta components. Those are the ones that are facing downwards. Reason for that is, look, if I've got a force here from over here on this side, there's going to be a matching force over here, and the lateral components are going to cancel out. Those sideways components are going to be gone, so we really don't have to calculate those. Again, by symmetry, those sections are not going to add up to anything. They're going to completely cancel out. So I'm only keeping the downward component, and that's what's reflected here. Now, the force acting on a current over a certain length, the force acting on a current over a certain length in a magnetic field is given by that formula. We've got to scale it down because we've got to go in and add together all the little tiny df's. So I'm going to, for a little bit of length, I'm going to get a little bit of force. So that's tricky sometimes, identifying which one of these values, the I, L, or B, needs to get scaled down. And I'm thinking, if I think in terms of little sections of this loop, well, the magnetic field remains finite at every location, and the current remains a finite value at every location. So it's really just the L that scales down. I'm going to call that ds. Now it's ds along a curved path, so that can be replaced with r d theta. So that looks like how we're going to add together all the little df's, or how we're going to designate how much force is in each df. Now remember, we've got to just take the cosine theta component. Okay, I think we have to go to the next page. I think we covered everything here. And then these are the df's that we want to add together, just the ones in that lower region. Let's take a look here. So there they are. I substituted in I, B, R. There's my cosine theta, and then there's the d theta that we had written down. So this is exactly the df with the cosine theta factor multiplied in. Carrying out that range of integrations gives me IBR2 sine theta naught, for what it's worth. So that's how much force we'll have in the downwards directions. So if that is, I don't know, how do we maximize this? Should be at 90 degrees, right? So at 90 degrees, if we went all the way up to here, oh yeah, that makes sense. Because if we go past that, we're going to start getting some cancellation. So the largest force we would have is if we carried this out to 90 degrees, and that's it. And that would give us 2 times IBR would be the force that we would have from that. Okay, another thing we could check is what happens if theta naught is 0. And for theta naught equals 0, surprisingly, we didn't have any force. Because none of this is in a magnetic field. So a couple of things we could check. I did go back and do the lateral components, just to show that in this case, the lateral components cancel out. Okay, so let me move on. As I was saying, I probably put more examples in here than I should have. Let's see. Here's a good example for following the trajectory of a charged particle in a magnetic field region. Now, did I draw this? I think I drew this in. So I drew the magnetic field, here it is, into the page. And then I brought in the helium nucleus. Now, the helium nuclei have 2 protons, and it depends on which isotope it is. Now, by far, the most common isotope is helium-4. And so the mass here would be 4 atomic mass units. It does depend on the isotope. So the circle, the radius of the circular motion of the charged particle in the magnetic field will depend on what the mass is, and different isotopes would have different masses. So anyway, I picked the 4 isotope, or they did. Let's see, what mass did we end up with? They gave us, no, I guess I calculated this mass. Anyway, they gave us roughly that mass. They wanted this isotope. So here comes the charged particle in. And I wanted it to enter the magnetic field and then be able to do complete circles. And so the idea here is I'm just going to catch the edge of the magnetic field, and at some point this gets pulled in, and then once it's in, I want it to be able to complete circular motion, and that's just to be able to solve the problem the way they described it. So this is problem 19. Now it says that in order to speed up this helium nucleus, we used a voltage of 2700 volts. So this takes us back to electric forces and electric potential and potential energy. I hope you guys remember all that, because that does get included in some of these problems. Something like that could easily get in, not something super detailed, but you know, this calculation is a good example. So for a voltage of 2700 volts, the kinetic energy that the nucleus acquires would be Q times V. That would be 2E times 2700 volts, which is 5400 EV. Now we've talked about EV as these energy units that can be useful for kind of at the particle level. If I'm looking at an atom or a molecule or something like that, that can be handy. But since we're going to need more than that, we're not just calculating energy, I need to get this in joules. So I redid this with a charge of 2e, but this time I put it in coulombs, multiplied by the voltage, I got the kinetic energies, plugged it into my kinetic energy formula, and then I put in the mass. So this is the mass of helium-4, checked everything, made sure I did a square root, and it said that these helium nuclei are coming in at 510,000 meters per second. So that's it. That's the speed that these things are traveling. Now, we've derived this formula enough times. You should be able to derive it. I should say that too. So if you had an exam and it said, you know, derive the formula for the radius of a charged particle in a uniform magnetic field, yes, you should be able to derive that. But I'm just writing it down here, putting in the mass, the speed we got now, the charge we have, it's 2 plus charges, and then the magnetic field. That gives us a rate. Ooh, it's only 3 centimeters. So this thing's coming in and it's going around in 3 centimeters. Well, a little, about that size. So it's going around in circles like this, right? They're pretty small. And then it wants to know what the period is. How much time does it take to go around and make one of those loops? And you go, well, these circles are pretty small. It's just these little tiny circles, and it's going really fast. So I'm guessing it doesn't take very long. I put the circumference, that's the distance, divided by the speed, followed it all through, and actually along the way I calculated a rotational velocity, 16,400 radians per second. It only takes 383 nanoseconds to make one of those loops. Okay, so this is happening many, 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 many times. What do we got here? 3 million times. Yeah, 3 million times every second, something like that. It's a lot. It's going really fast. All right. Problem 25. Yeah, I know, I'm moving pretty quickly here. Maybe I'll end up finishing too quick. Problem 25 is a chance to go in and just completely do all the vectors in components. So what they've done in this problem is they've given you a region. There's a region where there's an electric field and there's a magnetic field, both present in the same region. And so these are the components that they gave us. Now, I like writing this in vector notation, Ex, Ey, Ez, Bx, By, Bz. And so these are just the numbers that they gave me. Now there's nothing in the z direction, that's nice. Magnetic field, same thing, nothing in the z direction. And so here's my little picture. I drew a picture. Here's the region that I'm thinking about. And everywhere in this region, wherever I look, there's an electric field, and it's got those components, which means at every location it's oriented kind of like this. It's got this positive x component and this negative y component. And so those are all the E fields. Now, they're both overlapping here. So also in that very same region, I've got magnetic fields, right? And these, if I look at the components here, it's positive x, positive y. So that's going to be angled diagonally like that. Okay, so you know, in these problems, we always like to be able to do drawings and see what's going on. And sometimes that gets really, really hard. So I'm already a little panicked here because I've got 3 components of electric field, well, 2 components of electric fields and magnetic field to keep track of in this region. Fortunately, there's no z components. Now, what they want us to calculate is this. A proton, a single proton with a charge of 1.6, 10 to the minus 19 coulombs, is traveling at a given instant. So things are happening fast here because of all the electric and magnetic fields. These protons are being redirected constantly. But they're saying at a particular instant, we do a snapshot, and right at that time, the proton has components of Vx, Vy, and Vz given by these numbers, 6,000, 3,000, minus 5,000. So now I do have a z component. Okay. So the velocity is in all 3 directions, and at this point I'm thinking, oh my gosh, it's getting pretty hard to visualize what's going on here. I got too many things going on in too many different directions. So what I can keep track of, that's fine. What I'm not keeping track of, well, let's see, we've got plus v Vy minus, so I've got some velocity here and some velocity kind of in that direction. So the velocity is more similar to the direction of the magnetic field. Okay. Now, they want us to get the force. So I'm going to calculate the electric force, which is Q times E, and that gives us these components of force, Fx, Fy, Fz, for the electric force. And these came out to be 10 to the minus 16 newtons in terms of magnitude. Now you're thinking, I know you're thinking, well, that's a tiny force. 10 to the minus 16, that's a tiny, tiny, really, really tiny number. But these are protons. So these protons have tiny, tiny masses. A force that size for a proton is going to have an enormous effect. It's going to be a huge acceleration for that proton. Anyway, the force of the electric, the electric force is not too difficult, because when I come back up to this region, remember we had a proton kind of going through like this, maybe back in the negative z direction. There's going to be a force trying to redirect it in the direction of the electric field. So the electric field oriented like this, the protons are positive, they're going to feel a force right in the direction of the electric field. So these components are going to match up with the electric field, not too difficult. But then there's the magnetic force, right? With the magnetic force, I got to do a cross product. I got to do a cross product of velocity and the magnetic field. And at this point, I think I'm losing it, right? I think I'm losing track of what direction this would be. And in any case, here is the cross product formula. Now I wrote it out. I wrote all the components out because I think that's important. I think that's a good way to remind yourself how these things work. So here is the force in the x, the force in the y, and the force in the z, and that's what you got to do to calculate. So there's a good number of steps here to keep track of. I got to take the right components of v and match them with the correct components of magnetic field. Now when I did that, in general, if you're just randomly throwing numbers in, the forces due to the electric force and the force due to the magnetic force aren't necessarily going to be the same order of magnitude. It depends on what the magnitude of these are and the velocity. Well, somebody planned this out, I think, because it turned out when you calculate the force due to the magnetic effects, that also came in at 10 to the minus 16. Okay, I don't think that's a coincidence. Somebody set the problem up so that you would have similar forces from both. So anyway, I think I did this carefully. I think the answers match the back of the book. You guys should check and see if this worked. Anyway, I got components for the magnetic force. And what was kind of interesting is they're kind of in the same direction. The forces are actually in similar directions. Let's see what happened here. There was a velocity going like this with some z direction. I guess it was the z direction that made the difference. If I have z and, boy, that sure seems backwards to me now. I wonder if, well, I checked everything. I think it's correct. I think it matched the back of the book too. All right, we got to move on in any case. You guys can check the numbers here. I was just thinking, if we had a velocity in the negative z direction. Oh, I was using the wrong hand. Sorry. Okay, that's a problem with the right hand rule, is if you're using your left hand, you're going to get the wrong answer. Okay, sorry about that. That would have worked fine if it was an electron, but it was a proton. So let's try that again. So if I've got velocity into the board, fingers in the direction of the magnetic field, the force is going to be that direction. So kind of roughly, both forces add together, and then I added them, the F net was combining the electric force components and the magnetic force components. It's a good problem to think about. It's a good problem to keep track of, practice keeping track of all components, okay? Especially with the magnetic force, which you got to carry through that cross product and keep everything straight. All right, here is another example. that, that I'm looking at here. It's 27, problem 33, and we've got a charged object. It says it's a proton again. These protons get around. So here's this proton coming right to this location, and there's kind of a sharp edge to this region where there's a uniform magnetic field. Now that's a tough thing to produce. So it's hard to get, a magnetic field that turns on and off, right? But anyway, they've done it. And so we've got this magnetic field here, but it just drops off right here. So out here the magnetic field is 0. Now, one of the reasons I put this on the list is because it was listed as a type 3 problem, and you guys know, going through the homework, that our author, the textbook, has ranked different homework problems. Some are ranked as being more difficult, some as being more not so difficult. This was ranked as type 3, which is the most difficult category, and it really surprised me because it's not. This is not a true type 3 problem. Let's see. So they said that this comes in at 45 degrees, but I generalized that. I said, well, wait, maybe we don't have to jump to conclusions. Maybe we can just put a theta in there for now and see what we can figure out. Now, if I put theta in here, as soon as it reaches this region, that proton is going into circular motion. I hope that's circular. So that's a circular section right there. And circles have centers. So what I can do is I can draw a perpendicular, a tangent to that line right there. Not a tangent, a perpendicular, sorry. Perpendicular to that line, and come back a distance radius. I know that this proton in the magnetic field is going to end up with a constant value of little r. So I put that little r in there. And then what's going to happen is it's going to go in circular motion until it reaches the edge over here. Now that's going to be when another length of little r matches that center. Now that means that if I look at the entrance and the exit point and then follow lines back to the center, I've got an isosceles triangle. I've got a triangle with side r here, and then I've got this side here. And that side there is length, we called it x, it is labeled x, 2r sine of theta. So it's theta on both sides, it's isosceles. So a little bit of symmetry in this example. And circles, it shows up in circles, right? Maybe you guys have seen this in other examples where you've got circles, and if you keep track of where all the radiuses are, sometimes those diagrams simplify, and that's what's happened here because we don't have to put anything else in. We can immediately say that angle matches that angle. So they want to know what angle it exits at, and it exits at the same angle that it entered at. Now, as far as calculating what the value of x would be, what we can do is go in and get an r value. That's the formula. So now it comes down to determining r, mv q over b. There's my proton mass. See, the proton mass is really tiny in kilograms. That's how fast it's coming in. It's coming in really fast, 130,000 meters per second. There's the charge. There's the magnetic field. I ended up with a radius this time of 1.60 10 to the minus 3 meters. So this radius is 1.6 millimeters. So it's like that. So there's got to really be a sharp edge on that magnetic field, right? Because it comes in, and within a couple millimeters, it doesn't go very deep into the magnetic field. This is only going to come in like a millimeter or something. Not even a millimeter, maybe, because that's 1.6 millimeters there. So depending on how I drew that, probably about a millimeter of depth into the magnetic field. It's going to get curved back. And then for their angle, they gave us an angle of 45 degrees. It worked out to be 2.26 millimeters. So it goes in and it exits the magnetic field a little over 2 millimeters downstream. Anyway, type 3 problem. You're going, yes, I need more type 3 problems like that. This wouldn't be bad to have on the midterm, right? This isn't such a bad problem to take a look at. All right, let's see. Problem 37. So this is dealing with Earth's magnetic field. This is kind of an interesting problem. So first of all, we did this in lecture. Here's Earth. Here is Earth's magnetic field. And Earth's magnetic field has a shape or a geometry to it that is a dipole shape. And by dipole, what that means is it's equivalent to, or very close to being, equivalent to a really, really powerful bar magnet that's down deep inside. We don't think that's where the Earth's magnetic field comes from. But anyway, the geometry is fairly simple in terms of magnetic field geometry. So here's this dipole shape to it. And that says that, you know, I think most people are used to thinking the magnetic field kind of runs parallel to the Earth's surface because, hey, you get a compass out, and you hold the compass, and the compass, you know, goes back and forth, and then it settles down in some direction that's roughly north. But it turns out that the magnetic field lines only run parallel to the surface in regions near the equator. If you get very far away from the equator, and we're far enough away to definitely see this effect, most of the magnetic field, the largest component of the magnetic field, is actually downwards if you're in the northern hemisphere. And if you're in the southern hemisphere, the largest component of the magnetic field is upwards. You know, how do you know when you found magnetic north? If you're an explorer and you're out looking for magnetic north. When you get to magnetic north, the magnetic field is directly down into the ground. So it's direct. So you get out a plumb bob and the magnetic field runs right along that very same line. At the South Pole, the magnetic field is directed exactly out of the ground with a level region. So anyway, what they tell us in this problem is we're in a place in the Earth's, on the surface of the Earth with a magnetic field of 55 microtesla. Now that's not an unusual number. You know, Earth's magnetic field, the magnitude does vary from location to location, but you know, 55 microtesla is a pretty reasonable number, 50 microtesla, somewhere around there, for many regions along the surface. And then it says that it has a 66 degree dip angle. So what that means, let's put it on a coordinate system. Let's say that we're looking at an up-down coordinate system. This direction is north and that direction is south. So it's like I am, let's see, in here, north is like this direction. So the graph I'm looking, yeah, it's like having a graph here in front of me, and north is to my left and south is to my right. Maybe more like that. South is to my right, and this is up and this is down. So don't get up and down mixed up with north and south. It's unfortunate we do that. So here is the north component along the surface of the Earth, and here is the downwards component, and there's a dip angle of 66 degrees. So what that says is, at this location we're looking at, the north component is 22.4. I put the sine and cosine factors in. Oh, I didn't show. So the north is going to be cosine theta and down is going to be sine from the diagram. So 22.4 microteslas north and 50.2 microtesla downwards. Okay, so that's the first part of the problem, is getting yourself oriented as to what components of magnetic field do we have. All right, now the intention is we're going to take some loops of wire. Now this is a different view. This is a top view. What we've done is we've taken 12 loops. There we go. I got the 12 loops in there. Yes. The 12 loops are written down. I'm running 7.1 amps. I've got my loops of wire hooked up to some power supply, and I'm running 7.1 amps through my loops. That's a pretty good current. And then the radius, this is not resistance, that's radius, is 0.09, it's 9 centimeters. So 0.090 meters. And that's what they tell us. Now, so what I did was this. I took each one of these components separately, because what they told us in the problem is we're supposed to be looking for a torque being generated by magnetic forces. So How is that going to work? Well, if we run current, they said current is running counterclockwise through these loops. So what I did is I just did a bunch of right-hand rule stuff. I said, look, if I've got current, all the magnetic field should be into the board. I have a hard time doing the right-hand rule with. So I guess it's like this. So here's the velocity, magnetic field's coming out, and is that right? Oh, the magnetic field is here. This is B north. So B north, so we're looking at the surface of the ground now, and just to make sure we're oriented now, I'm looking down onto the ground. North is over here, and north is that direction, south is there, west is here, and east is here. So those are all directions along the surface of the Earth. I'm looking down onto these loops. And what we're predicting is, if I've got a magnetic field here, let's see, current is here, magnetic field there. The force is what's coming out of the page, not the magnetic field. So I'm going to have forces lifting this off the surface if it's large enough. There's still a gravitational force holding it to the surface. But if the magnetic field is large enough, or the force is large enough, and the object's not too heavy, you could imagine lifting this edge of it off the ground. Now this part's being lifted up, this part's being pushed down. So that's being pushed down into the earth. It's going to push against the ground, it's not going to push itself into the earth. But so the north component is creating a torque on these loops of current. So the north component's creating a torque. Let's see what the downward component is doing. So again, I'm looking downwards. So now the magnetic field is oriented into the page. And when I do the same analysis here with the forces now are uniformly radial. So if I look at these forces generated by the down component of the magnetic field, they all cancel out. So what we've identified here is that it's the north component of the magnetic field that is generating the force for us. The downward component is not giving us a torque, not just a force, but it's also giving us a torque. Okay, so we can take one more look at this, I guess. Here is my north component, here is the downward component, here is the magnetic field. Now, we've been looking at individual components, and I always think that's a good exercise to go through. Go through the individual components and identify those magnetic forces and see where they are. It turns out that, in the textbook and in class, we have derived or kind of shown that the torque can be written as a dipole times the magnetic field, where the dipole formula is given by N times I times A. So they've given us N, they've given us I, they've given us A. We can calculate what the magnetic dipole is, and for these loops, these 12 loops of wire with current running through them, it's a magnetic dipole of 2.17 joules per Tesla. Or the joules could be written as newtons per meter, because we're really interested in using torque units. That's what we're after, is finding out how much torque we have. And so the magnitude of that torque, using that vector equation, the magnitude of that would be the magnitude of mu times the magnitude of B times the sine of the angle between them. So here's another way we could go back and solve this. The magnetic dipole direction is directed into the ground. And that's because we have the current running counterclockwise. So, using a right-hand rule, we defined positive current directions and negative, and this is like negative current direction, and that means that the magnetic dipole is oriented downwards. So it's this angle I want. This is where the magnetic field is. This sine of 24 degrees is what I want. Well, that's the same thing as just picking out the north component. So this part right here, the magnetic field times the sine of 24 degrees, that's the north component. Okay, that we looked at on the previous page. Now, it's not the dip angle. So the dip angle we were looking at before was up here. That was, so cosine of 66 is the same as the sine of 24, is what we're looking at there. All right, and the torque then worked out to be 48.5 micronewton meters. So it's not a very large torque. Okay. All right, how are we doing here? I realize we're going through these at a pretty good clip. You can slow this down. You get out the lecture notes. And all right, we're moving on into chapter 28. So here, oh look, it's Laney the Eagle is here again today. Laney's right here with us. I hope, checking all the steps on these things. Let's see. This is a parallel wire problem. So I got two wires, current 1, current 2. Now I labeled them current 1 and current 2 because they're in two different wires, and I want to keep the wires straight. But it tells us in the problem they both have the same current going in, and they're both 35 amps. So 35 amps, that's that's a pretty good amount of current going through these wires. The wires are separated by a distance. So the distance here, we're calling R, we'll see why. That's 4 centimeters or 0.040 meters. And then we're looking at a 25 meter length of these two wires. So these wires just run side by side for a good long distance, 25 meters. Now in the book, I realize in the book, this formula shows up and they just kind of hand it to you and you can just plug into it if you want. But what we would like to do, what I'd like to do in this example is break it down into 2 steps, because these kind of formulas, these one fell swoop formulas are fine for when you are in these simple examples, but when you get to more complicated examples, you're not going to have those. You're going to want to be able to break this down into 2 separate steps. So here are the 2 steps. Step 1 is, and we talked about this in class. Step 1, find the magnetic field due to current number 1. Now if I ignore current number 2, I just ignore it. I erase this, it's gone. If I'm just looking at current number 1, I can ask, what's its magnetic field look like? Now the magnetic field surrounding a long, long wire is given by 2K over C squared current through the wire, 1 over R, where R is keeping track of a radial direction away from the wire. Okay, it's kind of cylindrical symmetry with the wire running down through the center of those cylinders. Now I put all the numbers in. I was able to come up with, I never calculated, I should have done that. Oh, that's too bad. Anyway, put the numbers in here and calculate the magnetic field. I always feel like it's good to be able to see those intermediate steps. Let's calculate what the magnetic field looks like, and then let's calculate the force. So this is what the field looks like surrounding that wire. And then once we've got the magnetic field, now we don't have to calculate it, we can just look at that formula. What we're going to do is specifically identify a region through that magnetic field, and now we're going to bring wire 2 back in and allow current to run through wire 2 through that region. And we're going to make sure that this is spaced at 4 centimeters. So step 1 was getting a magnetic field formula due to wire number 1. And then step 2 is calculate the amount of force. And the force is going to be I2L times B1. So if we merge those 2 equations together, this equation and that one over there, we get the equation that they've derived in the textbook. So, and then I did plug all the numbers in and got the force, 0.153. Now, we want to make sure we get the directions. So this is getting the magnitude of the force. Let's make sure that we're clear on the directions of the force that we're going to have here. So the first step in that is getting the orientation of the magnetic field due to current number one. So current number one, if I use a right-hand rule, I'm going to get a magnetic field that goes into the page, loops back behind, and comes out of the page here and then loops around. So if I follow those magnetic field directions, they're going to be looping like this with the wire going right through the center. So I've drawn all my X's here to represent at that location going into the board, and then here coming out of the board. So if wire 2 is placed here, then what will happen is the force will be in the direction of current cross the magnetic field. So if the current is my thumb and the magnetic field are my fingers, I've got to put my fingers pointing into the board, and that's going to give us a force in this direction. So wire 2 is going to be drawn towards wire 1. What happens when we reverse things? What happens when we flip that around? And you go, yeah, it's got to be the wire 1 is going to be attracted to wire 2. Now it does turn out with magnetic fields, forces are not always equal and opposite, but there's enough symmetry here that really wire 1 and wire 2 are in the very same environment. Okay, if one's experiencing an attractive force, the other one's got to be experiencing an attractive force also. Okay, so if you did, that's a good exercise. Go back through, start with I2, calculate its magnetic field, and then calculate the force on current number 1. All right, here is looking at problem 19, looking at the magnetic field along the region directly between two wires. So I got two wires. They've got currents I1 and I2. Again, they match. And both of those currents are coming out of the board. These wires are very, very long. So once again, for these wires, we can use the formula we've derived from Ampere's law, 2K over C squared I times 1 over R. Now what they want us to do here is actually look at different points between these two wires and calculate the magnetic field. Now for any individual wire, let's say here's one individual wire right here, if I'm looking at points moving away from the wire, I'm going to get magnetic fields that are perpendicular to that path. It's perpendicular to that R thing, so that's what's happening with the wire here, is the magnetic field, due to wire number 1, is oriented in this direction at every point. Now they're getting weaker because there's a 1 over R in that formula. So if we ignored wire 2 right now, those are all the, oh, that needs a B1 right there. So there's a 1 there that's missing, needs to go in. Now for wire 2, what we could think of is, on this very same diagram, wire 2, if I start going in this direction, because that's where we're looking relative to wire 2, the magnetic fields are going to be pointing directly downwards. Okay, so none of these angles are too difficult. Everything's just tipped at a right angle. So I can just use the right angle to show that the two contributions of the magnetic field will line right up. I don't have to do any complicated vector addition. I just have to subtract. So since if, which is the case they give us, if the two currents are the same, then their fields will cancel right in the middle. And then as I get closer to current 1, B1 will dominate. And as I get closer to current 2, B2 will be the larger. I set up a different coordinate system than they used. I always like something a little more symmetrically placed. I put x equals 0 in the middle and called this x equals plus a and this x equals minus a. They called the whole distance d. But you, when you solve the formula that way, you don't quite see the symmetry in the same manner. So I just put the two contributions. I put a contribution in the positive direction from here, from I1, and then going in the negative direction, measuring distances out away from I2, and then combine those algebraically to get this formula, and graphing it, it looked like that. Now, again, what that's referring to is what's the magnetic field look like as a function of x. It's superimposed onto this diagram. What it's saying is if I'm over here, the magnetic field is very large and in the positive direction. Once I get to here, complete cancellation. when I get to here, very large but in the negative direction. Okay, is what that's indicating. So adding two magnetic field contributions together. Okay, so that's a good skill. That's a good thing to do, practice adding those magnetic fields together. In problem 29 from chapter 28, we have, we're constructing a solenoid, and the solenoid's going to have a length of L, and it's going to have a radius of R, so we're going to get started with that. And then we're going to make the solenoid out of a piece of wire and a cylinder. So we're going to have a cylinder that we're just going to wrap the wire around. So they can be pretty simple devices. And it says that the length of wire we have to make our solenoid is 20 meters of wire, and the wire diameter is 2 millimeters. So it's 2 millimeter diameter wire that's 20 meters long. And then that's what it's going to look like when we get through. Now, we don't know how long it is yet because we haven't wrapped the wire, we haven't calculated. We do know that the solenoid, once we get it completed, we've derived this formula. The magnetic field in kind of the central region of the solenoid will be given by 4 pi k over c squared n over L times I. So we're set up to calculate that. We just need to come up with, now they told us the current, I didn't write it down, 16.7 amps. So we just need to get N and L. That's just a bunch of constants. And I've got those all written down. So the way we're going to do that is the radius of this, they tell us that the outer radius needs to be 2.5 centimeters. Now, the wire itself is 2 millimeters in diameter. So I'm going to come in from each side and drop that down to 2.3 centimeters, 2.30 centimeters for a diameter. Now if that's the diameter, then the radius that we're going to use is going to be half of that. So again, we started at 2.5 centimeters, 2.50. We came in a millimeter on each side. That took us down to 2.3 because we want to measure out to the center of the wire for measuring the distances. So we're going to have to measure the circumference of the wire, and so we're measuring from the center of the wire at 1.15 centimeters. Multiplying that by 2 pi, we got 7.23 centimeters. Now what I can do to count a number of loops is take my 20 meters of wire, see that really long piece of wire, divide through by the circumference. It says I'm going to have 277 loops, roughly. So 277 loops. And now the length of this is going to be 277 times the thickness of each wire. And that means that the solenoid is going to be 55 centimeters in length. So it's only, 2.5 centimeters wide, but it's like 50 centimeters long. So it's a really long cylinder. It's got a small R and a big L. Anyway, putting all the numbers in, the magnetic field worked out to be 10.5 millitesla near the center. Okay, we have a couple problems here at the end. I wasn't sure whether to include these or not. These are tough problems. These are genuine type 3 problems, maybe type 4, 4.5. There are some harder problems here. I feel like they're kind of useful, so it's probably, it's well beyond, I think, anything that would show up on a midterm. But let's just take a look at this. It says that we have a rotating charge disk. And the first thing they want us to do is say, okay, if I have a bunch of charge uniformly distributed over this disk, how much magnetic dipole does that correspond to? Now, our formula that we've derived in class for a magnetic dipole is I times A, but that's where all the current is following a circular path. In this case, with the disk, we have to add the effects from many, many individual circles. So each circular ring is going to have a contribution of d mu, and that's going to be the area for that ring, and the area is going to change. Little r is going to keep changing, so these areas are different. And then the current is going to be, that little bit of current in that ring corresponds to how much charge divided by the period. So that's charge per time crossing a point. That's what current is telling us. Now, we've done this before with circular disks. The dq is total q times d area over total area. So I got to keep track of all those factors. Here we go. So each one of these little du's, that's the area factor. This is the period. Ooh, that's the item here that I left out. So the period is 2 pi over omega. So where I had the di, it's being replaced by dq and t. T is being replaced, the period is being replaced by 2 pi over angular velocity. And then the dq is being replaced with this. Okay, and I factored everything out. There were constants q omega over r squared. And then I had 3 factors of little r. 2 factors here from the area, 1 more factor from the area of that thin circular strip. And I plugged everything in. That gave me an integration of 1 over 4, r to the 4th between 0 and r. I carried out the integration, and our prediction is that the magnetic dipole from a circular disk depends on how fast it's spinning, depends on how much charge it's got, and it depends on how much it's spread out. So a bigger r, if you take the same amount of charge, spread it out more, it's more dipole doing that. Now, just to give you guys a heads up for later parts of the problem, they're going to ask us about the magnetic field being produced. Well, if I use the dipole approximation for the field, the B field for magnetic dipoles we had looked at in class as being given by 2k over c squared mu 1 over x to the 3rd, and that's along the axis of the dipole, of the spinning dipole. Now what we would expect is that this becomes a very good approximation when we're far away from the dipole, but it won't get the details quite right. Okay, and so we're going to set this up again, and many of the same things we did for the dipole are still here, but this time we're not calculating the dipole, we're calculating the magnetic field along the axis of that spinning disk. And so we're going to set up one of these. We've seen these before with electric fields. I think we saw some in lecture 2 with the magnetic field. In any case, if I start from that circular disk, I pick a point and I draw a line. That's my radial unit vector. The disk is spinning this way, and that means right at that point the charge is coming out of the board. So that becomes my velocity unit vector. And then the magnetic field, which should have a vector sign on it, add that vector sign, is going to be in the direction of V cross R. I'm using my right hand this time, that's good. So V cross R is going to give us the direction of B, and then keeping track of this angle, we're going to get a cosine component and a sine. Now, the cosines are going to cancel out as we take complete circles, as we go all the way around that circle. So we're just going to ignore that and say the net effect from that circular loop will be dB sine. That needs to be a dB too, huh? So that is a dB, 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 dB sine theta. So here are the formulas that we've been using. Now, we've been using formulas either for current. In the book, this is listed as the Biot-Savart law. We added to that. They were just showing it how to do that in terms of current. We added to that. In fact, we started with, I guess we did it in reverse order. We started out just with charges in motion. And this actually is a good chance for us to come back and use that formula. We can come back and say I have a certain amount of charges in motion. Now, let's see how so the interval's set up. This is the interval we want to use. It says use this, so naturally we're going to. And then we just have to make a bunch of substitutions here. So let's see, V is going to change. The charges, as we get farther and farther out, those charges are going faster. So V, I'm going to write as R times omega. The whole disk is spinning with the same value of omega. But it's not the same v everywhere. So that will take care of the velocity variation. There's a sine theta factor. So where this sine theta factor is coming from is this right here. Okay. Now the cross product also has a magnitude, these unit vectors, but notice that the unit vectors are at right angles to each other. So I've got a radial unit vector here, I've got a velocity unit vector coming out of the board. They're at 90 degrees, so I'll drop those out and replace it with a factor of 1. So the sine theta is specifically coming from this effect right here, taking the magnetic field and dividing it into lateral and axial components. Let's see, what else did we have to change here? Now, little r, up here we said little r was just distance, but distance isn't going to work as little r because we need little r to keep track of the disk that we're integrating across. So what we really want is the distance. And the distance here is that hypotenuse, and that's going to be r squared plus x squared. So that's distance squared. Now I've got a sine theta, and the sine theta is going, here we go, sine theta is going to add on r over r squared plus x squared to the half, and then here is the expression for dq. We use that already in this problem. We use that in part A. Okay, that's a lot of pieces, right? So, and that's how setting up these integrations works. So we're going to take, this, make all of these substitutions that we talked about, bring all the constants out, and the constant's 2kq omega over c squared r squared. We're going to be integrating across all of these circular rings of charge, and that means integrating from 0 to big R. And then I counted 3 factors of little r. Let's see if we get them all right. There is a factor of little r in the velocity. As I get farther from the center, charges are moving faster. There's a factor of r in the sine theta. So that's also a factor of r in the numerator. And then there's a factor of r keeping track of the area of each one of the circular strips. So 3 factors of r, each one coming from a different effect, which is kind of interesting. See how much fun physics is? So in math class, you have these integrals that you set up, and they're interesting, but they're just math symbols. Here, every symbol means something. So, and what you can do is go, oh yeah, the speed is going to increase as we get, oh that's right, we're only going to be able to keep this component. So you can kind of see what's going on. Everything has meaning and attached to each symbol. Anyway, the integral turned out to look like this, and I had done so much work at this point, I boxed it. I said, that deserves being boxed right there, because that's a really pretty looking integration, and why not? Let's box that and show that we're feeling pretty good that we got to this point. Now, when it came time to carry out that integration, it was kind of hit and miss. I did not find, I tried a few things, a few tricks myself. So I think I looked it up eventually, or I worked back, I guess it was, from their solution. So I was able to show that, I was able to come up with an integration and plug in the limits. I guess I didn't put all the details here. When I carried out this integration, I plugged everything in. That was the exact solution. So that's what the magnetic field is along that axis. And we've idealized a lot of stuff here, but we're going to call this our exact solution because we haven't made any approximations at this point. All the formulas that we've done, starting from the Biot-Savart calculation of the magnetic field, everything should hold true. Now, what we want to do in the last part of the problem, and this is where things get really, really a little dicey here, a little sketchy here, is this is a prediction from the magnetic dipole that we did in part A, but that's only going to be true when we get far, far away. So what we want to do is we want to take our exact formula, see that one down there where it says exact solution, and look at the case where Rx is much bigger than R. So as we get far, far away, it should start to look like a little tiny dipole, and that's where that's what the magnetic dipole formulas are based on. So what we've got to do is this. On part C, again, we're going to take that magnetic formula that we derived, but we're going to look in the limit where X is much, much bigger than R. So I spent some time setting this up. This is the magnetic formula that we have on the previous page. But I moved a few things around. I simplified that expression. I think this looks the same. I don't think I pulled out any more factors. Now, since R is going to be much, much bigger than R, X is going to be much, much bigger than R, sorry, I'm going to factor out the big terms. See, that's going to be really big, that's going to be small. So I factored out a 2x squared, and that's what I got. Now on this one, again, I'm going to factor out the x, because that's the really big stuff, and so it's going to look like this. So I took this expression and I rewrote it. Now what I'm doing is I'm setting things up. We've done these approximations before. We've used this approximation of 1 plus u to the n, which you guys learned back in Calc 3b, I think is where you do that. So you learn how to do these series approximations. And so in the case where u is much, much smaller than 1, which is the case we have, what we're doing is we're going to write this down as a series. The leading term is a 1. The next term is nu. That's going to be much smaller because u is very small. The next term is going to be u squared, and and so forth. And so what happens is I'm going to take this expression right there, that thing that's in the denominator, and write it as 1 plus r squared over x squared to the minus 1/2, and follow this formula and write down the first couple of terms. Now, I had to write out 3 terms. I think I told you guys earlier in lecture we did this a few times. And usually we only had to keep 1 additional term. This time that canceled out. And so I had to go back and redo it by keeping 1 more term, and that worked. So I kept that extra term. So for all you math majors they're thinking, wow, this is really cool, right? Going back and using series to come up with a formula. All right, so I took, I rewrote the expression this way, and I am now going to take this expression right here, and these two together actually, these two multiplied by each other, and what I ended up with, here's that first term, that's not an approximation, that's exact. Here are the first 3 terms of this expression, so that's where the approximation is. And then I multiplied them together. Now the biggest term is going to be the 1 times the 1. I wrote that down. The next terms in my list are going to be the r squared over x squareds. So I have oh, I guess I got to go up here. I have a 1/2 r squared x squared times 1, that's plus, but I also have this product. And this product and this product, I wrote them down, but they cancel. And those are the only 2 ways that I can come up with r squared over x squared. So the next term is going to be keeping track of all the r to the 4th over x to the 4th. So to get those, I have, this is one possibility, is to take this product. That's going to be an r to the 4th over x to the 4th. And then I'll also have a 1 times 3/8 r to the 4th, x to the 4th. So I took those 2. And then looking at this, those are the only ways I can get r to the 4th over x to the 4th. Now, if we had kept additional terms out here, the next term here would be an r to the 6th over x to the 6th. And it would be much smaller. So what we've done is we've multiplied those 2 expressions together and then identified stepwise smaller and smaller terms, keeping the ones just as many as needed. Again, this canceled out, and that's why we had to go to this additional term. So it says that this entire expression in my exact formula can be approximated as 1 plus 1/8 r to the 4th over x to the 4th in the limit where x is much, much bigger than r. Plugging that back in to the original formula up there, Now I've got all that complicated stuff is being replaced with this complicated stuff, but it's a bit simplified. The 1 and the -1 go away. And we've seen that pretty much every time we've used these approximation techniques. The big pieces go away, and you're left with a smaller piece. This time it's really small because we skipped this part canceled out. We had to go to extra small. And so that's what we're left with. And putting everything together, there was a factor of 2x, and since the 1's are gone, I just have that 1/8, which came from these two terms. So that's the 1/8, r to the 4th over x to the 4th, and miracle of miracles, right? It matches. So once we did all of that really cool approximation stuff, we were able to show that in the limit where x gets much, much bigger than r, that the exact formula reduces down to the formula we would have for a dipole. All right, so it looks like we might have another 5 minutes or so. I've got one more problem listed. So let's take a look at that one also. I think I have one more. I think this is it. It is. We made it. I hope we didn't go too fast. So the last example is actually problem 44. I guess both of these were assigned. You need 41 to be able to solve 45. Let's say that we're really focused on 41. I think that's a more useful way to think about this. So 41 says this. It says that I have a current segment. There's a short section of current, and we pick a direction for that, and I said it has length b, because I like using little a and little b, you guys have probably noticed. And then there's a point out here that lines up with the end of that current segment, and I called that distance a. And I said, here's a little bit of current, a little ds, that's my ds right there, that's going to go into my magnetic field formula. That ds right there is going to be right there, and that's going to be dx. And then I identified where are my radial unit vectors and my velocity. Now the velocity unit vector is always in the direction of the current. And so that wasn't, every step of the way here, the current's going in that direction. So when I bring that unit vector up to this location, the velocity vector, it's going to be there. Now, the radial unit vector changes. So when I start over here, the radial unit vector was here, but as we integrate across this length, that keeps shifting. And we'll take that into account. So x I'm going to say is the distance from, I'm going to call that x equals 0, and measure x out to, well, eventually to b. So we're going to integrate from 0 to b. Now I just wanted to show that there's a mirror image of this, and I think this is the one that the book shows. When we do the mirror image, so instead of the current segment going from 0 to b, the current segment is going from -b to 0. And what you can show is that you're going to get the same contribution. So calculating one is the same as calculating the other. You can do it either way. You can do the limit from 0 to b, or the limits from -b to 0. You'll get the same effect. And the reason why is this. If you look at these unit vectors right here and take their cross product, well, v cross b is coming out of the board, and it's going to be the sine of that angle that determines how strong the magnetic field is. Over here, E and EV and ER, is that what I said? EV and ER are cross product of that is going to give me the magnetic field direction. It's also coming out of the board. The angle there is the supplement of the angle here, and supplementary angles have the same sign. So we're going to have the same contribution carrying out this calculation as we would carrying out this so we can work from either one. Now, back when we first introduced this, I think the formula we started with was we did a comparison with electric field calculations, and we said that instead of the electric field, we're going to call it the magnetic field, but to make the units match, we have to put in a factor of c. Okay, and then we wrote down the k2 over r squared. We said the magnetic fields are dependent on velocity, specifically v over c, is that ratio that we use for the velocity. And then it also depends on a cross product of unit vectors. So the formula we had, we used that dq in the previous problem. We used this formula. I had to keep the v inside. But this time we're going to go back and use the current formula. So just showing how we derived the Biot-Savart law. You know, in textbooks a lot of times they just throw it out there. They go, aha, there's this Biot-Savart law, and it doesn't look like anything we've ever looked at before. When, in reality, it's just a modified electric field expression. Okay, so we're kind of using the very same expressions we would use for an electric field, making an adaptation with the velocity factor. So we're setting everything up. We need to get distance measured. The distance from here to that point is x squared plus a squared. So we've got the distance in there. We're also going to pick up a factor of sine phi, because this time the two unit vectors are not perpendicular. So there is a non-perpendicular angle between those, and so the magnitude of our cross product will leave us with a factor of sine phi. So that's a different source of the sine factor than we saw in that earlier problem. So the sine factor is right there, and then it turns into another one of these integrations. This one wasn't quite as difficult in setting up, but that is the integration we have for this. And I looked this one up too in the back of the book, Appendix B, I think, and I plugged in all the values. So I looked up the integral, set the limits, plugged in the values, and this is what I ended up with. Is that the B field at that location is coming out of the page, and it's given by kq over c squared, b over a, 1 over a squared plus b squared to the half, where a is the distance away from the wire and b is the length of the current segment. Now this is problem 45 here, so we're just throwing this in at the end. So problem 45 says, if I have a rectangle of current, I didn't draw the current in, draw some current and some arrows. So there's current going through this, okay, and along that rectangle. What you can do is, it says you pick a random point at location x, y, and calculate the magnetic field at that location. Now, since the magnetic field is coming directly out of the board, what I can do is I can take the rectangle and divide it up into 1, 2, 3, 4, 5, 6, 7, 8 separate segments. And say, now I can just use problem 41. So I can go back and use the formula that we had derived in problem 41. And it gets complicated, right? So for these two segments right here, I started at the origin. They gave us a coordinate system. I started at the origin and did this one and this one, and substituted the values in. X over y, 1 over x squared plus y squared to the half. This one's y over x squared plus y squared to the half. And then I got to these two segments. And again, they're kind of, this is the inverse. These are going to be inverses. And then they share the same denominators here. I didn't put the other 4 in. There's more. Okay, I'm going to leave it there. So I think that's about it. I think we're through for the day here. So we do have the midterm coming up. We've you can go back and look at that review. If the homework reviews work well, go back and look at the review that we did for chapters 25 and 26. Here's one for 27 and 28. And then there's also review problems available for in general. So some previous year's midterm problems, take a look at those too. If you guys have questions, stop by. Have a good rest of the day.